All right, guys, let's try this again. The previous video I recorded while I was teaching did not work so well, so hopefully this goes better. So we're talking about acids and bases. Acids and bases. Now let's first look at the definitions. So we have two sets. Arrhenius' definitions as well as Lowry and Bronstet's theories. Let's start with Arrhenius, and these are obviously according to your exam guideline. So an acid is a substance that produces, that produces hydrogen ions, which are these ones, in aqueous solution. So basically what they're saying is that it increases the concentration of the hydronium ions when it's added to the aqueous solution. A base is a substance that produces hydroxide ions in aqueous solution. So in this case, what they're saying is that it increases the hydroxide ion concentration in an aqueous solution. Then we get to Lowry and Bronsted. This is the short version. Even though it's two names, it is the shorter definition. So in this case, an acid is a proton donor. Why a proton? Because that's what a hydrogen is if you remove the electron. It's basically just then the proton. Then a base is a proton acceptor. Now, when we do the conjugate acid-base pairs, you'll see where that comes in, especially. Now, let's look at the next one, which is a strong and weak acid. Strong and weak acid. So what is a strong and a weak acid? A strong acid, we say, ionizes completely in water to form a high concentration of hydronium ions. And examples of these are hydrochloric acid, nitric acid, sulfuric acid, as well as phosphoric acid. These are the ones you can definitely expect and should know. You have luckily been taught them since grade 9s. I mean, just the other day I was teaching my grade 9s these specific acids. So they are our strong acids. Then we get our weak acids. They ionize, but incompletely in water to form a low concentration of hydronium ions. And in this case, the example is ethanoic acid and oxalic acid. Now, here you see I drew an arrow, a one-directional arrow. Why? Because if something ionizes completely, it goes from being the acid into its ionic form. And all of it, all of the acid, as my reactants, change like that. Here by the weak acids, however, I have used a arrow going both ways. So we have a multi-directional arrow, meaning it is a reversible reaction. So not all of it ionizes. Some of it stays as acid, but it's going back and forth, back and forth. Okay. Keep that in mind, especially when we get to calculating the pH. Here, we now talk about strong and weak bases. So basically the same concept, just now we're talking about bases. So a strong base, instead of ionize, we say dissociates completely in water to form a high concentration of hydroxide ions. And your examples would be sodium hydroxide and potassium hydroxide. And also when you come across your reactions that you have with haloalkanes, like your substitution reaction and your elimination reaction, these are the bases that we also come across. Now, again, you'll see there's a one-directional arrow, meaning all of the reactants become products as the base reacts with H2O. Then the weak base dissociates incompletely in water to form a low concentration of hydroxide ions. And in this case, you'll have an example as ammonia. Ammonia is a weak base. Just remember that it is the exception to the rule. It doesn't dissociate like the other bases. It ionizes also. All right. And then calcium carbonate is another example of a weak base. Potassium carbonate is a weak base. And then also sodium hydrogen carbonate is a weak base. You'll again find that there is a double arrow there, which indicates that not all of it will be in its dissociated form. Nee, you'll still have some base left in the aqueous solution with some of it having dissociated. Or nee, okay. Then we move on to concentrated and dilute acids and bases. Now, it's important to be able to differentiate between a strong acid and a concentrated acid, or a weak acid and a dilute acid. So let's look at what is concentrated. So remember that concentrated means this. If we remember the definition, it is the amount of solute per liter of solution, right? So basically per liter of water. And if I make Oros for myself and I only pour in a little bit of the Oros into my glass of water, it's going to be dilute. But when I pour a lot of Oros into my glass, still a glass of water, it's going to be concentrated, because in that glass there is now more of that Oros. Same thing with concentrated here. If I have a certain volume, in our definition, it's a liter, so a certain volume, it depends on how much of my acid I add to it. Okay. So concentrated contains a large amount of acid or base in proportion to the volume of water with an R. So here is an example of a concentrated substance. Diluted, obviously, is if I now add more water, so the ratio of water to substance particle is greater. So the definition is it contains a small amount of acid or base in proportion to the volume of water. So this is more diluted than that one. All right. Now, that brings us to acid base. Again, if I'm going too fast, this is all revision from grade 11. And as I said, I'm teaching this to my grade 9s right now. And in all honesty, this is the work that my 11-year-old wrote about as well. So we're just revising. Now, acid-base reactions, let's quickly go check them out. Now, first of all, aqueous solutions of acids and bases. So that means if I now add my acid or my base to the water. So here I have my HCl, just a reminder, monoprotic. Do you guys remember what monoprotic means? So my HCl plus H2O. Do you see here, in this case, it's a gas, and this is a liquid, okay? Obviously, it won't always be a gas. Sometimes it can be in an aqueous solution. Then the concentration is obviously important. But all right, so HCl added to H2O as a liquid, they react, and then it forms H3O plus, aka hydronium ions, as well as chlorine ions. So this is how they ionize. Do you see the ions? All right. Then we've got ammonia, also as a gas, with H2O as our liquid. Again, remember with reactions, in most cases, it's only H2O that will be the liquid. The other ones is, although they look like a liquid, they're actually an aqueous solution. Then when it ionizes, it forms ammonium, which is NH4+, as well as hydroxide ions. So this is obviously a base. This is an acid. We know, obviously, because we've learned that hydrochloric acid is an acid, but we can see that what is produced is hydronium ions, meaning it will increase the hydronium ion concentration. In this case, what is produced? Hydroxide ions. So it will increase the hydroxide ion concentration. Then H2SO4 is diprotic. Why? Because of that little 2. Nee, diprotic, that little 2. And it is now reacting with water. And it also gives us hydronium ions, which increases the hydronium ion concentration, as well as the sulfate 2 plus, or SO4 2 minus. Sorry, I said plus, I meant minus. Right. And obviously the AQ refers to aqueous solution. Nee. Right. Now, conjugate acid-base pairs. So what is conjugate acid-base pairs? Well, in a reaction, you have two substances. So here I have HNO3 and it reacts with H2O. And now it forms NO3 minus in this instance and H3O plus. This we know is our acid. But if you did not know nitric acid, the first step in acid or conjugate acid base pairs is to identify a pair. So you need one from the from the reactant side to go with one from the product side. So if we go and look at which of my reactants match most closely which one of my products, I hope you can see that it is this one. See, HNO3 and then NO3 minus. So these two are a pair. Let's look at this one. Which two resemble closest? This one and that one. So they are a pair. Now, how to identify which one is a acid in my pair and which one is the base in my pair. So in this case, it is, well, in all cases, it's the one that has the most hydrogen between the two. So here it's HNO3, whereas here it's only NO3. So the one that has the most hydrogens, I also wrote it there, the one with the most H's is the acid. So this one's going to be my acid and this one's going to be my base. All right. Here's my other pair. Which one has the most hydrogens? This one does. So this will be my acid and this will be my base. Okay. Now, you'll know that H2O, hopefully, we say is an amphelite. Why is it an amphelite? What is an amphelite? So, sorry for the spelling error there. But an amphelite is a substance that can act as an acid and a base. It just depends on what it's reacting with. Now, our most obvious amphelite is H2O, but then anything that can either lose a hydrogen and still be something that we recognize, or gain a hydrogen and again still be something that we recognize, is going to be an amphelite. For example, if I were to take away a hydrogen from H2O, what would it form? It would form that, and we recognize that as a hydroxide ion. If I were to add a hydrogen, so that's one if I take it away, here's if I add it, then I would find that it's H3O+, and I also recognize that one. Here, HSO4-, and remember this is important, okay? Those charges are important, okay? You can't just leave them out and think it's still the same thing. It isn't. It's not. Yeah, you have to include them. So if I were to take away a hydrogen, what would I be left with? SO4, since it's minus, now I've taken away the proton, which is positive, so now it's going to be 2 minus. And we know this is a sulfate polyatomic ion. If I were to add a hydrogen, it would form a H, so it was 1, now it's H2, SO4, with no charge, because remember I added a proton now. Same thing here. If I were to take away a hydrogen, then it would form HPO4, 2 minus, okay? If I added a hydrogen, it would form H3PO4, and it's going to be neutral there. This one, as you see, is just the intermediate there. All right, so key thing about an amphelite, it has a hydrogen to either donate, but it would also be able to accept a hydrogen, and it still forms something that we recognize. All right. Then we get to neutralization reactions. So neutralization reactions are reactions between acids and bases. And in most instances, they form salt and water, but there are 2 exceptions. So let's quickly check them out. So first of all, the reason why we say acid and a base, because of this hydrogen transfer that occurs. Now let's look. So acid plus metal will give us salt. So here's the first exception, and H2 gas. Why? Well, let's go check it out. Here's an example. So here's nitric acid with its hydrogen to donate, because it's an acid. there is Na, so just the metal, Na. Then it forms the salt, and you see where the salt comes from? Always, the salt will always come from them. There's my salt. And now H2. Now, first of all, why not just hydrogen? Because hydrogen is a diatomic molecule, so it doesn't just exist as singular, right? It has to be H2. You won't just find the H floating around. So H2. Why not H2O? Well, this is a polyatomic ion, and as far as possible, we consider them as one thing. So polyatomic ions we consider as one thing, especially now, all right? So it will form here. That means we don't have an oxygen so that this can change to water, right? So because there's no oxygen present bonded with my metal, it's just going to be H2, okay? So not H2O, just H2. So again, if it's an acid and a metal, it forms salt and hydrogen. Now, if we, however, have an acid and a metal hydroxide, now we'll get salt and water. So H2SO4, sulfuric acid, with magnesium hydroxide. Now you'll see that this and that forms my water. All right, and then there is the salt. Next one, also acid plus metal oxide gives us salt and water. Let's see why. Because here's hydrochloric acid, there's magnesium oxide. Haha, and now this oxygen and hydrogen come together and it will form my water over there. So there's my salt and water. Okay. My second exception to the rule of neutralization reactions forming salt and water is acid with a metal carbonate. Because the moment that we now have a carbonate, a metal carbonate as our base, my additional product will be carbon dioxide. So HCl, there we go. So we have HCl plus CaCO3, there's my carbonate. So that together with that forms my water as well as my carbon dioxide. All right. Next one we're going to do is hydrolysis. So what is hydrolysis? Hydrolysis is the reaction of salt with water. So we just did neutralization reactions, right? And we saw all these different salts forming, all of these different salts forming. Now, if I were to add one of these salts to water, it would react with the water, it would react with the H2O. Now, that resulting aqueous solution will either be slightly acidic, slightly basic, or neutral. So how do I know which one it is going to be? Well, if it is a strong acid and a strong base that created the salt, that means my resulting aqueous solution from that salt will be neutral. If it was a weak acid and weak base that resulted in a specific salt, then that aqueous solution will be neutral as well. So strong, strong, neutral. Weak, weak, neutral. But if it was a strong acid and a weak base that formed that salt, the resulting aqueous solution is going to be slightly acidic. Makes sense, because it was a strong acid. If it was a weak acid and a strong base, then the resulting aqueous solution will be slightly basic. Okay. Which brings us to titrations. So what is a titration? Now, unfortunately, for those of you who's watching this video and couldn't be in the lesson itself, we did one in class, but I'm still going to show you what a titration is, because it's not the first time that you've done it. We did it last year as well, but if you do want to do it again, I'm inviting you to just make an appointment with me and then we'll do a titration together. But until then, let's quickly check out what is a titration. Now, titration is basically a technique, a setup that we use to exactly or precisely neutralize either a base with an acid or an acid with a base. And when I say exactly, I mean none of the two will be in excess. They will be perfectly reacted. All right. So the setup looks like this. We use a conical flask, first of all. So this is a conical flask. Now, a conical flask is shaped like a cone. Do you see? It's shaped like a cone. And the reason for that is because you're swiveling it. And if I were to do it in a normal beaker, then you have a chance of spilling some of your acid or base, which is not good because we want exact amounts, right? We have to work very precisely. So first we start off with a conical flask. Then, to make sure, as I said, that we're working very precisely, we're going to use a pipette. Now, the one that we did in class looked something like this, with a little bubble there. And a little bubble there. And then it said 50 milliliters. So you literally suck up the acid or base. So we take this, we put the exact amount, the correct measured volume inside of our conical flask, all right? And usually this one also, we know the concentration of. So we call this then the standard solution. So what is a standard solution? It's the solution, either the acid or the base, that we know the volume and the concentration of, all right? Then we're going to add an indicator. So this is my indicator, and an indicator, as you guys learned, tells us the pH of the solution. It depends on what you are titrating. That will determine which indicator you are going to use, and we're going to look at that now. All right. The one in class that we did is we placed our acid in here. So this was our acid. We used 50 ml of that acid, okay? And we had used a concentration of 0.1 mole per cubic decimeter. That was our standard solution. Then we added bromothymol blue. And the reason for that is we used hydrochloric acid. The next thing that you do is you take a burette. You guys have used a burette before. And we put our base in there. Okay, now usually you don't know the concentration of the base, or whatever you place in here, you don't know the concentration of. Can they be swapped? Yes, you'll still get your values, your answers. Okay, so now what I do is, because I've placed my indicator in here, so here's my indicator, it's going to be a certain color. Now I'm going to start adding, in our case, the base slowly. So it's going to start dripping in there until at one point it changes to the end point color. And an end point color tells me that the equivalence point has been reached. What does that mean? That means because of that specific color change, I know that the exact right amount of base was added to neutralize or react with all of the acid that is inside of my conical flask. And they have reacted perfectly in the correct ratio. So in my final beaker, I now can see, there's no more acid molecules, no more base molecules, only salt and water. So none of them is in excess. Okay. So which indicators do we use when? Well, if I use methyl orange, okay, it would be if I am titrating a strong acid with a weak base. Why? Because methyl orange is red as an acid, yellow as a base, but orange at its equivalence point. Okay, so the moment that it goes orange, I know, boom, they have been completely neutralized. I will use bromothiamyl blue for a strong acid with a strong base, or if I use a weak acid with a weak base. Why? Because bromothiamyl blue is yellow when it's an acid, blue when it's a base, and green when the equivalence point has been reached. And its equivalence point is a neutral pH, all right? Whereas methyl orange is a more acidic pH at its endpoint. Then, for a weak acid and a strong base, we'll use phenolphthalein. Why? Because phenolphthalein is colorless. Phenolphthalein is colorless when it's in an acid, pink when it's a base, and pale pink when the equivalence point has been reached. And that equivalence point is slightly basic. So do you see that the reason I use methyl orange when it's a strong acid weak base is because its endpoint is slightly acidic. Why do I use bromothiamyl blue when it's a strong and weak? Because its endpoint is neutral. And why do I use phenolphthalein when it is a strong base, weak acid? Because its endpoint is slightly basic. All right. So again, what is equivalence point? It is the point at which the acid has completely reacted with the base. So perfectly reacted. And that is also obviously true for vice versa, if it was a base with an acid. What is an endpoint? Endpoint is the point where the indicator changes color, right? Now, a formula we can use when doing titrations is this formula. Now, you'll see it's Na over Nb is equal to Ca Va over Cb Vb. And although I did also write here that Na is for acid and Nb is for base, it's not really necessary because it actually is for solution A and solution B, right? But if I now look at this part here, what do I substitute into my mole? I can substitute either the coefficient in my balanced chemical equation, or I substitute the actual mole of my acid and base. And why? Because of the titration method, the mole will be in the same ratio. Neither one of them will be in excess. Okay, so the mole ratio will be the same whether you use the coefficients or the actual mole. Then the concentration, like in our experiment, the concentration of the acid was known and the volume of the acid was also known. So that was our standard solution. We wanted to calculate the concentration of the base. And we got the volume of the base by taking my initial reading and my final reading. So this was my initial reading, and the difference was my volume of the base. All right. So that's how I got the volume of the base. And then this was my unknown, and I could calculate it, right? So if you want to try it yourself, you can do example question on slide 38 to 43. It's on the PowerPoint that I shared with you, but I also shared the pictures on the group if you want to go check it out there. Then our next part is pH and pH scale. So pH scale, what is pH scale? Now, hopefully you guys know this. At this stage, I know my baby that's like 11 did it the other day in school as well, and my grade 9s as well. So this is just revision. So a scale of numbers from 0 to 14 used to express the acidity or alkalinity, which is the same as saying base, of a solution. Now, just to clarify something that I see sometimes learners get confused with. If this is my scale and it goes from 0 to 14 with 7 being in the middle, my strong acids will be here. My strong acids. has low pH values. My weak acids will be closer to 7. But then my weak bases will also be closer to 7, all right? Whereas my strong bases is closer to 14. You see that? Okay, because 7 is neutral. All right. Now, how do we calculate the pH? Now, the method we're going to be first looking at is specifically for strong acids. All right. Why strong acids? Because we're working on the premise that strong acids ionize completely. All right. So these steps can be used only because strong acids ionize completely. Okay. Let's start with the formula. So the formula found on your formula sheet is pH is equal to negative log square brackets hydronium ions. So that just means the concentration of hydronium ions. So if I want to calculate the pH, I have to multiply the concentration of the hydronium ions with negative log. So negative log times concentration of hydronium ions. If they do give us the pH and they want us to calculate the concentration of the hydronium ions, we'll just use the inverse of this. All right. So please first start off with that, and then you can go to the inverse of it, which is this formula. It is not on the formula sheet. So if you don't know what the inverse of negative log looks like, yeah, just remember this formula there. Now let's look at the steps. So again, the only reason we can follow these steps is because they work on the premise that strong acids ionize completely. That means this: if I have a certain amount of acid molecules and I put them in water, all of those molecules will become hydronium ions, all of them, yeah, because they ionize completely. So the first step, if we want to calculate the pH of an acidic solution because of a strong acid, then we first need to calculate the concentration of the acid. That we do either with the titration formula that we just did previously or with stoichiometry. Yeah. Once we have that, we now can calculate the concentration of the hydronium ions that we would like to substitute into our pH formula. How do we do that? So to get the concentration of the hydronium ions, we look at the acid. If the acid is like HCl, we call it monoprotic. Another one is nitric acid. Also, it's monoprotic. So what does that mean? That I have to multiply the concentration of my acid that I just calculated with 1. Right? Because for every 1 molecule of acid that I've now added to the water, it will form 1 hydronium ion. Okay? If, however, the acid is not monoprotic, meaning 1 hydrogen per molecule, but instead is diprotic, di referring to 2, which is this little 2 there in sulfuric acid, which is our example. It's H2SO4. That means to get the concentration of the hydronium ions, we have to multiply the concentration of the acid times 2. Why? Because for every 1 molecule of H2SO4, I'm going to get 2 H3O plus ions. Okay? If it's triprotic, such as phosphoric acid, that means I have to multiply the acid concentration by 3 or with 3 to get the concentration of my hydronium ions. Why? Because for every 1 molecule of H3PO4, the moment I put it in water, it will give me 3 hydronium ions. All right. Now that I have the concentration of my hydronium ions, I can substitute it into my formula right there and therefore calculate my pH. And to check this out as an example exercise, you can look at slide 49. We're quickly going to pause before we get to calculating the pH of a strong base, so we can quickly just understand this concept. Now, here's our formula. We have the constant, the equilibrium constant for water, and it is equal to the concentration of the hydronium ions multiplied with the concentration of the hydroxide ions. And that gives us 1 times 10 to the power of negative 14, and this is at 298 Kelvin. Okay, so that is our equilibrium constant for the autoionization of water. So what does that mean? What is autoionization of water? Well, if you think about it, because water, we said, is an amphibolite and it can react with itself. That's what water does. So you're thinking your glass of water is sitting there all chill. It's not. It's reacting with each other. Okay. So water reacting with water. Now, this is a reversible reaction forming hydronium ions, plus OH. Don't know why I put those there. Overzealous. Don't put them there. Okay. So now what we'll find is if I were to go and write the Kc value for that, I am going to say it's the equilibrium constant of H3O plus and also the OH minus. And then I should put it over my reactants, nay. But look, my reactants are liquids, so I'm not going to include them in my formula, which is where we get this formula from. No, there's no reactants at the bottom because the reactants is the water, which is a liquid. Okay, so just to explain basically where does that come from. Now, what is the definition? The equilibrium constant for the ionization of water. Okay. Autoionization of water, what is that? It's a reaction of water with itself to form H3O plus ions and OH minus ions, so hydronium ions and hydroxide ions. Okay, you with me? Now, let's go calculate the pH of a basic solution, but with strong bases. Remember, strong bases? And again, the reason we can use this method is because strong bases dissociate completely. Now, here are the steps, and you'll find that they are very similar to our previous steps, with one exception. Now, step number 1, calculate the concentration of the base. So whatever base is in our aqueous solution, sodium hydroxide or potassium hydroxide, or whatever the base is, whatever the strong base is, we first go and we calculate the concentration. Again, using either titration formulas or just stoichiometry, we go and calculate the base concentration. Now, if the base is monobasic, now you don't need to know that term, but that just means there's one hydroxide, right? So where is it? Yeah, just one hydroxide. It's like sodium hydroxide. Then you know that the concentration of my hydroxide will be equal to one times the concentration of the base. If it is dibasic, that means there's like OH2. That means that I'm going to have to multiply the concentration of the base with 2. If it is a little 3 there, then I'm going to have to multiply the concentration of the base with 3. Okay. Now, once we have that, and this is now where that extra step comes in, once we have the concentration of the hydroxide ions, we cannot now substitute it into our formula that I've showed you previously. By the way, this formula is found on the formula sheet. So yay, all right, as well as this formula is also found on the formula sheet. Now let's get back to it. So now we have the concentration of the hydroxide ions. So the first thing we're going to do before we go to the pH formula, we first now need to find the concentration of the hydronium ions. So we're going to substitute it into our formula that we just learned concerning the equilibrium constant for water. So we're going to substitute it in there, and then our only unknown variable will be the hydronium ion concentration. So that's why we'll be able to calculate the hydronium ion concentration. And now we substitute that hydronium concentration in this formula and we'll be able to find the pH. Just remember, keep an eye out. Your pH in this case needs to be greater than 7, a lot greater than 7, because it's now going to be a base. And please follow exercise. Do the exercise that's on slide 51 as another example. And this brings us to basically the only new work regarding acids and bases for grade 12. And that is your equilibrium constant for acids and your equilibrium constant for bases. So what is the equilibrium constant for an acid? Now this comes in when we are working with weak bases, although I have seen them ask it in terms of strong bases as well, which is why you'll see, or strong bases and acids in question papers, which is why you'll see I removed the part that says it's only for weak bases and acids. Like I said, I've seen in question papers that they have asked this regarding strong acids and bases as well. So what is the equilibrium constant for an acid? Well, it describes the extent of ionization of the acid. In other words, it determines the acid's relative strength, right? Meaning, obviously, we have weak acids, but some weak acids are stronger than other weak acids. And that's what our equilibrium constant for acid will tell us. Okay, so if it is high, we know that it is a stronger weak acid, if that makes sense. And if the value is low, it's a weaker weak acid. Because if it's a stronger weak acid, it ionizes to a large extent, but not completely. Right. Same thing for our equilibrium constant for bases. Describes the extent of dissociation of bases, and it determines the base's relative strength. So again, if I have a high value, then my base will dissociate mostly, although not completely. Whereas if I have a low value, then my weak base will dissociate to a smaller degree. All right. Now, an example, again, slide 60 and 62 that I've shared on the group. Just go check that one out. But here is if I now had to go and calculate the equilibrium constant. If this was my formula, just a general formula where this represents the acid, there's my water, here is the ion for my acid, and this is obviously the hydronium ion. So they will go here, and my acid here will go at the bottom. Now, why don't we include the H2O? Because it's a liquid name. For a base, same thing. If I have my base plus water, then it would gain the hydrogen there and add in a hydroxide or create a hydroxide ion, and then they will go at the top, whereas this one will go at the bottom. Again, please don't include the water because it's a liquid. All right. And that brings us to the end of the work that we did. The next video will be about part 2 or lesson 2, where we went through the past question papers. If you don't have those yet, you can come and fetch them in my classroom, and also I shared them on the group. Okay, bye.